Okay, in this video we're going to take a look at the cube root function. And in the same way that the square root function was the inverse of the y equals x squared function, the cube root function we're going to see is the inverse of the cube function, or y equals x cubed function. So this graph right here, this kind of, it's like almost like a skinny chair looking picture. This graph is the graph of y equals x cubed. And if we take this graph and if we reflect it across the line y equals x, just like we did before with the y equals x squared function, then we will get the cube root function. So let's see what this looks like. If I take this graph and I'm going to reflect it across the line y equals x. So let's see. That part's going to look like that, and then I'm going to take this part, flip it over here. And I'm going to have something that looks kind of like alright, so this graph that I've got here in red, that's the cube root function. It's the inverse of the cube function. And now before, if you recall when we did this inverse of the y equals x squared function, we saw that we had a problem because it failed the vertical line test, which meant that our new function wasn't actually a function. So I noticed though when I look at this new function, this function that I reflected here, this function in red, well, it turns out, no, it does pass the vertical line test, because I can see anywhere I draw a vertical line, it's only going to hit this red graph in one place. So I don't have any problems with this new reflected function, my cube root function. So this function, which by the way, that's y equals the cube root of x, that's that red graph there. So my cube root function, it doesn't have any problems, so I don't have to do this, this trick where I only look at, part of the graph. I'm going to look at this whole piece, the whole thing, for my cube root function. So let's take a look at some characteristics of the cube root function. So just like before, we're going to look at these 6 characteristics: the vertex, or the anchor point in this case, domain, range, in behavior, asymptotes, and symmetry. So the vertex of this function, again, this is my cube root function, y equals the cube root of x. And my vertex, or my anchor point, I'm going to call it, that's just this point right here in the middle, which is at 0, 0, the origin. My domain and range, so my domain is all the x values that my function can have. My range is all of the y values that my function can have. And once again, for domain, I'm going to ask myself, can I put walls around my function? And I notice if I try to put walls around this function, well, my function is just going to keep going in both directions. I can't put any walls around it that are going to keep the function in. So I'm going to say, then my domain must be all real numbers. So I'm just going to use this kind of funny looking capital R. I can have positive x values, that's all these values here. I can have negative x values, and I can have x be equal to 0, so x can be any real number. For my range, again, I'm going to ask myself, can I put a ceiling or a floor on my function to keep it in? And the answer is no. If I try to put a ceiling on it, then my function is just going to go through the ceiling. If I try to put a floor on it down here, my function is just going to break through the floor. So I can't put a floor or a ceiling on it, which means I can have any positive y value, I can have any negative y value, I can have y be 0. So y, turns out, can also be all real numbers. Now in behavior, remember we talked about before with the square root function, we said what happens to the value of the function, that is, what happens to the y values as x increases and just keeps going on and on and on. In other words, we said as x approaches infinity, well, what happens to y? And I can see that in this one, very similar to the square root function, as x keeps getting larger and larger and larger, y, it turns out, also gets larger and larger and larger. It just keeps going up and up and up. So we say as x approaches infinity, y also approaches infinity. Now for this graph, I can actually talk about end behavior in another way as well. That is, I can ask myself, well, what happens to my function as x begins to, I can think of it as x approaches infinity in the other direction. In other words, as x keeps getting larger and larger and larger in the negative direction. And the way we write this is we would say, well, what happens to my function as x approaches negative infinity? In other words, as we let the negative values of x keep getting larger and larger and larger. And again, I can see from my graph, as x begins to get more and more negative, it goes in this direction. Well, my y values, they start going down and down and down. In other words, they keep getting more and more negative as well. So we say as x approaches negative infinity, I can see on my graph that y is also going to be approaching negative infinity. So that's the end behavior of my function as x approaches negative infinity, as x goes in this direction. Asymptotes, again, this function does not have any asymptotes. So we just say none. And symmetry, now this is an interesting function because I noticed that while there's not anywhere that I could draw a line that will give me reflection symmetry, in other words, I can't draw a line anywhere so that I can create mirror images on both sides of the line. However, if you notice the way this function is drawn, it turns out that I could pick a point. Turns out it's this vertex point, the anchor point. I could pick that point, and if I were to rotate my function 180 degrees, well, it would just rotate right back onto itself. In other words, if I were to take my paper and turn it around, my new function, my rotated function, would look exactly like my original function. And we call that rotational symmetry. So I'm going to say symmetry, I'm going to say rotational symmetry. And those are the characteristics of my y equals the cube root of x function.